We are planning a session with 4 speakers in the order that you see there. Professor Shimon Ullman from the Weizmann Institute, computer science, Professor Hagai Bergman from the Hebrew University, our Parkinson expert, Professor Olaf Blanke from the EPFL, École Polytechnique in Lausanne. He will tell you about some amazing things, and our young comer, Dr. Amir Ahmedi from the Hebrew University, will tell you about sensory substitution. So I'll give you a 7 minutes, very fast introduction to the issue of augmenting cognition. I'll explain what does it mean to augment cognition. I will tell you that in the 21st century, one of the most challenging things in terms of brain research will be to not only heal the brain, but also improve the brain in order to enable it to face the upcoming challenges, which are going to be amazing. So this machine will have to learn constantly and adapt constantly to the ever-changing environment that it itself generates. Not to speak about diseases that will be coming, so we'll mention that. So I want to explain to you that in 7 minutes. Then I'll call Professor Shimon Ullman, and each speaker, if they will behave nicely, they will give exactly 15 minutes talk, and you will have 5 minutes after each speaker to ask questions. So that's the plan. Do prepare questions, because the whole notion here is really to interact with you rather than to have a monologue and go home. The interaction is very important, so please really ask questions. You have a one-of-a-lifetime chance to speak directly with the speaker, so please do it. And if there will be time left at the end, we'll have discussion together, but I doubt it. So let's start. So in the last 200 million years, there is this phenomena of the mammalian. We are part of the mammalian world, and this mammalian world is about 200 million years old. And during these 200 million years old, we as human beings, as Homo sapiens, we generated an unusually big brain relative to its own body weight. So in terms of brain as a size, we have other animals that are bigger than us, for example, dolphins or elephants. But relative to our body weight, this is the biggest brain we are aware of. That's the biggest thing, is not the important thing, but it's part of the thing. The fact that we are big in terms of brain is part of the capability to generate new things, but this is not the only thing, and we'll talk about this in a second. What makes us so unique? Why is our brain so unique relative to other brains of the chimpanzee, for example, that we generate all the time new things? Just to tell you that our brain in the last 100,000 years genetically have not changed, so we are the same genome like the early Homo sapiens 100,000 years ago. So we as a phenomena are very young phenomena, 100,000 years old, and all this yellow part, so these are years, all this yellow part is what we call the cultural evolution. This is a period where there is no genetic change in the human sapiens, but still we generate completely new things constantly. For example, written language in the last 5,000 years. So language and math is a new phenomena of this old brain, old in terms of 100,000 years old. So we are constantly generating new things like mathematics, science, computers, and we are also trying to understand our own brain. So this is an amazing phenomena, that the brain itself is generating tools to understanding itself, not only understanding, but changing itself, not only itself, but its own genome. It's a very unusual phenomena. We don't know of any other brain who is doing it. Just to tell you, not to be worried, but your brain is becoming less weight, less heavy with time, not now when you hear the talk, but on average, along the years, you can see that the brain was on average about 0.5 kilograms. It's less now. We don't completely understand why the human brain is becoming shrinked. Doesn't matter, because you see, we do amazing things with the shrink brain. But that's a fact that you could discuss in another session, not today, what is called the structural plasticity of the brain. Structural, the change in the anatomy of the brain with time. I'm not going to talk about this, just to let you know, your brain is not going to change, but the next generation will have a little shrinked brain relative to you. So this brain is doing amazing things, really. Absolutely shocking. All these things that we can do you know, Einstein and others, thoughts, creativity, imagination, art, mathematics, science. But on the other hand, this brain is doing other things that I want to discuss in a second. This brain of yours, like all mammals, have a unique thing, and a unique patent. We can say like an inventful building block. It's called the cortical column. So below your skull, in the cortex, this convoluted sheath of neurons have this kind of blocks, building blocks, repeatedly building blocks. Each one is about a cubic millimeter. This is called the cortical column. This is an invention of the mammals. We don't know of this structure before the mammalians. This is a new structure. We have it, mouse have it, monkeys have it, cats have it. Lower animals do not have it. And this is the first focus of the modern research in many ways. Not only, of course, because there are other parts of the brain, as Hagai will mention later, but the cortex is something very unusual for the mammalians. So we are trying to understand this column. We know today to simulate in the computer this column. So this is what happens in a millimeter cubic in your brain. A cubic millimeter in your brain looks like this, about 4 kilometers of wires, about billion, 10 to the power of 9 connections. This is the fundamental building block of this relatively new region, the neocortex. So now you are diving into a cubic millimeter in your brain. We have to understand all this in order to change the brain, to manipulate the brain in diseases and so forth. So the diseases is, of course, the main issue, because as we get older, as we expand life, we see more and more of these terrible diseases. We know today by names, we know today about 560 diseases are named, neurological diseases are named. And this is, of course, a huge suffering to the human being. I'm sure everybody or every one of you know that there are these diseases. He knows it from family or friends and so forth. And it's certain that it's clear that if we are going to expand life, and we do, the expectancy is that about the end of 21st century, we will live on average more than 100 years on average. This means that all these amazing, terrible diseases will come up, and we really need to solve it as brain researchers. We cannot allow ourselves to have a community with half people suffering from diseases like that. So that's the main issue, that's the main challenge, that's the main force that we are all putting in brain research towards the 21st century. We can talk about two aspects: the brain repair, repairing the diseased brain, you will hear about that today, but also to augment the brain capabilities. Because one thing, as I showed you before, is that with this same brain, we are changing all the time, constantly. For example, after this talk, you are certainly not going to have the same brain as you came in, if you will remember anything that I was just saying, or anybody else. So that means that physically your brain has changed. So this is a fantastic capability to change constantly with the interaction in the environment, with new challenges like GPS, with new challenges like iPhones and computers. And the challenges are going to become amazingly intense, really intense. We will have to adapt to all this if we want to go on living in this adapting and changing world. And this is called basically the brain augmentation. We are trying to find ways to enable the brain to be able to prepare itself, to be ready to the changes that our brain itself is causing. The new building, the new GPS, the new telemetric communication, and so forth. So this is the whole issue of brain augmentation. How do I intervene with the brain? Either by education, or by medication, or by electrical stimulation. How do I intervene with the brain to enable it, or do I want to intervene with the brain? How do I interact with the brain from the outside to enable it to expose, to express, to be able to challenge itself with the new things that are coming? So this aug-cog era, augmenting cognition, aug-cog era, is the era that we are in terms of brain sciences. It will impact every one of you. And so that's the session today. It will discuss the issue of augmenting cognition, both in disease, but also in health. I just want to say that we are optimistic that we can learn the brain, understand the brain deep enough in order to be able to repair it when it's sick, but also enable to use what we know, what we've learned about this, and make it more adaptable, more plastic, more capable of changing. And this is partly because of these new technologies. I'm not going to go into details. For example, the brainbow technology. It's a new technology that enables us to look at the brain in a colorful way, so the brain is not going to be any more black and white or gray matter. It's a colorful matter today. We can generate mouse, in this case, mice, that are colorful. It's called the brainbow technology. And this enables us to study the brain in a much, much better anatomically and also physiologically way. And this is a reflection of what I just said. These new technologies is reflected by many, many new brain centers in New York, in Jerusalem, now built by Norman Foster, in Lisbon, the Champollion Center in London, and so forth. There is now 10 new buildings being built today for brain research in a very different brain research that we used to. It looks like this. A center of brain research today will not be anymore a biological center. It will be an integrative center with physicists, computer scientists, engineers sitting in one center, interacting together to really solve the issue of brain research in general, but augmenting cognition in particular. These are the speakers that I mentioned before. As I said, Shimon Ullman from Weizmann will talk more about intelligent machines. Professor Hagai Bergman about deep brain stimulation in Parkinson and other diseases. Professor Olaf Blanke, as I said, is speaking about cognitive neuroprosthesis. This is very interesting. And Amira Mehdi will tell you about how can we see when we are blind, so to speak. When we are blind, how do we see through the years? So I'm inviting Shimon Ullman to give his 15-minute talk. Thank you very much.
Okay, welcome everybody. While this is being prepared, I will talk about the cooperation between brain and intelligent machines. And this is an area of study that progressed over the last several years at an amazing speed. And I would like to tell you a little bit about what has been happening and what we can expect in the future. As you will see the slides, the initial plan was to talk in Hebrew, but I realized at the last moment that while I was here, that there are many people in the audience who are probably may have difficulty with Hebrew. So I will talk in English. Some of the slides are exclusively in Hebrew, but I think that as I present them and explain what's going on, people who cannot follow the Hebrew, Hebrew writing in the slides will be okay. And Idan, where are you? If you can give me a two minutes warning. Oh, there is here. Okay, thank you. Okay, very good. So, the study of the attempt to create machines that will be intelligent and will be able to think on their own started from the very early days of the pioneers of computer science. I will mention in particular Alan Turing. This is the picture of Alan Turing, because now this year in 2012, all over the world, it's called in computer science the Turing year. He was a fundamental pioneer in the field, and we are celebrating 100 years to his birth. And he was one of the, while he started many of the theoretical aspects of computer science, together with this, he was an early pioneer of trying to build machines that will rival the human brain. Things started slowly, but the question I want to examine now, without giving a conclusive answer, is: are we now at the dawn of a new age of truly intelligent machines? We already had a number of great successes throughout the recent years. Perhaps the best known one, which really made a splash in 1997, where the computer called Deep Blue, constructed by IBM, managed to beat in international competition for the first time the world champion in chess, Garry Kasparov. The score was 2-1 with 3 draws out of 6 games. So the machine became for the first time the best playing system on our planet, better than the world champion. This was extremely impressive, but at the same time there is something limited about it, because chess is a very specific, focused, narrow domain. And the question is, can machines do something which is closer to the human brain, which be very flexible, creative, learn new things, and so on, which is not what Deep Blue was able to do. So after the years since 1997, I think that the biggest splash, just because of the limitation I mentioned right now, came last year in 2012, when a machine built again by IBM called Watson became the world champion in a game called Jeopardy. And those of you here who come from the States will probably recognize what this is all about. Here in Israel, most people maybe didn't hear about Jeopardy, but it's a very popular television game, basically a quiz, and it's completely open, so almost any question can be asked. The questions are difficult and tricky, and it really takes a subtle mind and a lot of intelligence to be able to play this game well. So IBM decided to build a machine and then to openly put it on the stage, and you can see here two human beings and one computer. This is connected to a computer. There is no person there, and are competing neck to neck. The question is being read out, and whoever answers first wins points, and so the thing continues. And after 3 days of intense competitions, many questions being asked and answered, the computer won. Watson became the world champion in this open game, and proved that machines, intelligent machines, can deal with very open, flexible domains. Let me give you one example of a question that actually happened during this competition. It's written here in Hebrew. In May 1898, Portugal celebrated the 400th anniversary of the arrival of this traveler to India. The answer, I don't know how many of you immediately know the answer. The answer is Vasco da Gama. Watson answered it in a split of a second. And the interesting thing was that there was no explicit mentioning of this fact in Watson's database. There were bits and pieces in various ways. For starters, you have to walk back and understand that it's a 400th birthday, so you should go 400 years earlier and look for events at that age, and so on and so forth. Everything came together very quickly, and Watson did it immediately and better than humans. Now, this is a game, but you can imagine what this kind of ability can do to real systems. For example, IBM is now applying it to medical diagnosis, and you can think about going to a doctor and just imagine that you know that the doctor has such a system helping him, that anything that was ever written in the field of medicine about a particular disease you might have, it's there. The doctor may not know about it, but the machine will, and will make the right predictions and connections and so on. So that's really can be a very helpful thing to have in real life. So this is up and coming, but if you think about it, we have already intelligent machines in our daily lives. Google search and other search engines are quite intelligent. Another example, a small example, but a telling one, in the States there is a video renting service called Netflix that rents out videos, and it makes very good recommendation. It guesses what each person is going to like. And this guesses what people like based on a variety of parameters is a complicated issue. Here is showing you a part of the formulas inside of how this Netflix makes it guesses of what people are going to like. So it's a complicated domain, and if you think about it, being able to have models of people and being able to predict what people are going to want and to enjoy is a very interesting capability. Last example, just because it appeared last month, just a few days ago in the New York Times, there was a system which was put to work in the school system in various places in the United States. The newspaper piece was called "The Algorithm Didn't Like My Essay." It's an automated system that reads student essays when they finish high school and grades them instead of human graders. A thing which is close to my own area of investigation is building machine that will be able to see. We all know about cameras that can recognize faces. There is a new camera out there that can recognize pets, for example, and it can shoot a good photograph of your cat or dog. It's really already in existence. There is a technology now in new cars doing driving assistance, can warn about the driver from obstacles, other vehicles, pedestrians, and so on. It's interesting to note this particular one because perhaps the leading company in this domain, serving companies from BMW and Volvo and Honda and many others, is an Israeli company called Mobileye, which was developed by Amnon Shashua, professor at the Hebrew University. It's a leading company, the leading company in this domain. And this is just the start. People are now experimenting with driverless cars. There is a car there which does not have a driver and can drive along the road. And people are talking about it seriously, that they're not too distant future. This will be sufficiently mature, this technology, to think about, a blind person entering a car and telling the car, take me to work, and it will be able to do it. In hospital as well, and so on. Now, the study or the development of intelligent thinking machines is a collaboration between two major areas of science, brain research on the other hand, and computer science on the other. So these two together are deeply involved and intimately involved in the science of creating intelligent machines. And the interactions go both ways. The brain teaches us about possible ways of what intelligence is and how to build machines, and machines are helping us to understand in a new ways, construct theories and understand in new ways the information processing that is going on in the brain. This collaboration between brain on the one hand and computers on the others has really taken off tremendously. To give you just one example, there is now in Europe, there is a competition for mega grants, for mega projects, two huge projects. Each one will be a scientific grant that will receive €1 billion to run the research program. There has been first round, there are 6 finalists in this competition, and 2 of these finalists, one is a large-scale simulation of the human brain in supercomputers, and the other one is the construction of intelligent robots with human capabilities. One reason or one change in recent years that is one of the driving forces behind this emerging tight cooperation between brain and computers are new abilities to image and see the brain in action. Until recently, the ability to see and investigate, study the human brain has been pretty limited. Most of the brain studies have been conducted on animals where experiments can be done. But with new techniques, we can now image the human brain in action. For example, using this machine, which is called fMRI, functional magnetic resonance imaging. This is a sort of an MRI machine, but the little f in front, this f, stands for the word functional. What it means is that rather than seeing the structure of the brain, you can see the function of the brain, which part of the brain is now active. So I can tell you, inside this machine, think about a particular poem by a poet you like, and you will see which part of the brain this poem sort of exists and activated when you recite this poem to yourself. Through this machine, one can see maps of the entire brain in action, and you can see here what a scientist looking at the machine while the person is in there and performing a task. One can get maps like this which give you in real time the full activation of the entire brain. And an amazing thing that has been done recently, this is used for for answering many interesting questions, but one in particular which is interesting to see is the ability to reconstruct the human sensory experience from the brain activity. So what we see here is what scientists have done, showing a person an image. In this case, is this French policeman or whatever this image is this. But the experimenter doesn't see this image. The experimenter just sees this map of the human, the subject activity, the subject who is looking at the image. The brain is activated. This is the brain activity. And having read this brain activity, it is now possible to reconstruct what the person was actually seeing, and you can see the quality of the reconstruction. So this is what was reconstructed from the brain activity. Here is another example, and there is a full movie, a person watching movie, and the reconstruction. So this shows how one can now understand and interpret at least some of the brain activity, and it brings in interesting questions. For example, would it be possible with this technique to read out dreams? Because during dreaming, nobody knows from the outside what you're doing, but recording brain activity and performing this kind of reconstruction, maybe we can follow in real time and see what a person is dreaming about or thinking about. So you can see that this is 2 minutes. Okay, so this is the next to last slide, so the time is working well. An area I'll just mention very briefly, but just to show you, it's not something that we have made a lot of progress in, but it's something we are starting with the scientific community, but showing you sort of the ultimate at what kind of interesting things open up. When we look at the brain, one surprising thing was that how the brain activity is divided between conscious, aware activity and unconscious activity. It turns out that a lot of activity, when you're thinking, looking, and so on, can go on in the brain without you being aware of what's happening. So some brain activity leads to consciousness and awareness. Some other brain activity, for some reason, does not lead to awareness and consciousness. So the whole business of can we look at the brain, distinguish between the states of the brain that lead to conscious awareness, those that not, and get a handle, start to try to understand how these subjective experiences, consciousness and so on, can come out of brain activity, and consider the fact whether intelligent machines of the future, can we expect that they will have some sort of awareness as well. So to sum up, what's next? In the near future, it's clear that intelligent systems will enter our lives more and more. They will have larger and larger influence on our society, on our economy, and so on. And as I said, these advances will come from a tight integration between brain science and computer science. So brain centers or scientific centers that have this collaboration will benefit. In the further future, it's clear that systems will become more and more intelligent, more and more clever, and in many domains will probably be more clever and more intelligent and more capable than humans. We will come to count on them and trust them more than we trust our own judgment, like in the medical diagnosis I mentioned before. It's unclear, but an interesting question, will they ever develop any kind of awareness similar to the kind of awareness that exists in our own brain? And finally, what will be the long-term influence of such a situation on the individual psychology and on society when we live amidst machines which are as intelligent as we are, and in some cases maybe even more? Okay, so thank you very much for your attention.
Your turn now. Questions?
I'll be more than glad to take any comment, question. Yeah, at the back there. But just speak up so that people can hear. Okay. She asked, what are the dangers? I think especially when, in light of the last slide, with all this, living along this highly intelligent machine, or just the slide before that, that one can look into a human brain and in some sense see what the person is thinking about. That's, it certainly has some scary parts. And I think this is like many scientific discussions. In a way, it goes beyond science. I mean, there are tremendous things. We can increase intelligence, we can help people, we can solve problems, and there is a lot of promise, and people are excited about the great promise. Like in many great inventions and scientific advances, there is danger. Invading privacy, using it for the wrong purposes. And as I also mentioned, even without using it for the wrong purpose, just what it does to the psychology and to society living this completely new situation. There are dangers, and I think that's one conclusion from this is that it's not just science, but these things should be discussed, and that's one reason why I think for us, as scientists, are really glad to discuss it and bring it out to the open and tell it to the public, is not just because we are happy to talk about our interesting work, which is certainly a part of it, but I think it's really an important mission, if you want. I think that these issues should be discussed, and this presidential conference is certainly a good place to do at least a little bit of it. Yes?
In this whole huge universe of research, what is the focus in Israel on what you're doing, and what is the role of the new centers of research excellence in this context?
Right. So the Israeli connection. Israel is really a leader both in the theory and I think in the practice of these things. In Israel, both in Jerusalem, the Hebrew University, at the Weizmann Institute, where I come from, for many years now, they were very early on in this wave of connecting theoretical computer science and brain research. And Israel is considered a leading country among the scientific countries of the world. In fact, Idan may know that better than I do as a person who is involved with the ICNC. It was selected in Europe as the best educational program for students in brain and computation, right? So there are many programs in the world studying, combining brain and computation. There was some evaluation committee, and they selected the Hebrew University one as the best in the best in existence. So Israel is leading, or is certainly in a leading place, along with of course other larger places, and in the applied applications of this as well. I mentioned, for example, Mobileye, the computer vision company, but it's not the only one. And the centers are very helpful in making this larger, and in particular, bringing back good people, which is a major, major thing. We have some wonderful Israelis out there. If we can bring some of them back, it would be great. And this is part of what these centers are doing. Yeah?
You talked about intelligence. What about wisdom? I think that the one thing that is the most important thing is thinking outside the box and not just playing chess, but rather having some creative thought and things that might be more complicated than just...
I agree, and I think that we are not there yet, but I think that the huge jump between the two big successes that I showed, sort of the chess and this Jeopardy, and the Jeopardy can really exercise some interesting judgment. It's still not an automated scientist and so on, but it's really impressive. People, if you ask people in the field, when IBM started working on this project, whether it will manage to win Jeopardy, my bet is 9 out of 10 would tell you no way, that it's too difficult. So even we are surprised that the rate that things are going are progressing. So we'll see. You're completely right that these are the uniquely human and important aspects of the brain, but I see no limitation. Things are getting there.
I'm sorry that we have to, I'm sorry, Shimon will be outside, we can talk maybe with him later. Sorry.
Right, so thanks again for your...
I will prepare himself. I just wanted to mention that responding to your question, we have to remember that we are physical machines. We are an example of the type of computer, not this type of computer, but a computer that has microchips and has electrical signals, and we can do all that we can do with it. So a physical machine can feel, think, imagine, create. We are an example, and I think Shimon will agree that we, because of this communication between computer science and brain research, we learn from the brain how to build intelligent machines, copy ourselves in some sense, deeper sense. So eventually the machine should be able to do what we do. Oh, sorry. Chagai Bergman is our, as I said, expert in Parkinson and beyond. Thank you for coming, Chagai. I know that you are running from one country to the other.
Thank you, Dan, and thank you everybody for coming. And as Dan say, I do believe that we are machine, but we are machine with a soul, with nefesh. And actually, the main question that I'm asking myself and we are asking society, are we able to treat the disorder of the soul and can we provide medicine to those patients that suffer from not only from neurological disorder, but also from mental disorder like severe depression and schizophrenia. And to do so, actually I'm going to start with one of the most classical neurological diseases that we are very familiar with, Parkinson's disease, and then I will move to the mental disorder. So Parkinson's disease was discovered about 200 years ago. We are very familiar with this because it is very common, actually, because it is about 1 out of any 100 person in the population above the age of 60 that has Parkinson's disease. And we know the disease. The main symptom for the disease that we are very aware are the tremor. The patient is tremor, but even more severe are the akinesia, the lack of voluntary movement, the fact that the patient will sit near a table like this and will speak very, very slowly and will not interact with the environment, will not get outside. This is the lack of voluntary movement. The akinesia, the lack of kinesia, is the most severe problem that we are facing with Parkinson's disease. And it took some time, but eventually it was discovered that Parkinson's disease is caused by the death of a specific group of neurons in the brain, the neurons that create the neurotransmitter dopamine, and this was discovered in about in the first half of the 20th century. And eventually people were taking this discovery and say, if dopamine is missing, then we can cure our patient by giving them back dopamine. And this was coming actually in the 70s. And dopamine replacement therapy, when we give our patient dopamine in order to cure their Parkinson's disease, is the gold standard of our therapy today. However, we are facing problem with dopamine replacement therapy. For the first 5 to 10 years, it's great, okay? But then after 10 years of treatment, most of our patients will develop the side effect of the dopamine replacement therapy, and they will have too much involuntary movement. They will move all the time, Michael J. Fox, that probably you've seen it on the TV, and so on. So the dopamine replacement therapy is great for Parkinsonian patients for the first 10 years, but after 10 years, we need something else. And eventually, the story came, the second stage of therapy for Parkinson actually started about 20 years ago when we have used a monkey model of Parkinson's disease. And in this monkey model, we've shown that by inactivation of a small part of the brain, the subthalamic nucleus, we can cure all the Parkinsonian symptoms of the monkey, the lack of movement, the akinesia, and the tremor, and we've been very, very happy with this. And 3 years later, this was taken to the operating room of human patient. And you know, one movie is better than 1,000, than many words. So what I'm going to show you, I'm going to show you a movie of one of these patients, and you can see soon the patient so. Yeah, okay. So, are you playing? Okay, great, thank you. And you see now the patient before the surgery, the way it looked before the surgery. So you see the tremor of the hand, you see the shuffling, very, very magnetic stepping, the way the patient is walking, severe difficulty in turning around. And now you will see the same patient after the surgery, and this is the patient, okay? And Of course, this is the best typical example, okay? This is done by the Medtronic company, okay? But this is what we call best typical example. But, but eventually, okay, can you get back to the presentation? But eventually, this deep brain stimulation neurosurgical treatment for Parkinson's disease is now actually our standard in the United States, Europe, and Israel of treating Parkinsonian patients with severe Parkinson's disease. In Israel, it is part of the national health program, so everybody can get it. All over the world, more than 100,000 patients have been treated with this kind of surgery. And here in Jerusalem, we've done more than 400 patients by now, and there are other programs going on. So at least one part of, or one disease of the brain, we've been doing very well with deep brain stimulation, with electrical manipulation of the activity of the brain, and we are able to provide, I would say, an hope for patients with Parkinson's disease that cannot tolerate anymore the dopamine replacement therapy. The only problem with a deep brain stimulation program is that it is not easy to manage the patient then after. What we do is that we are putting these 4 electrode contacts into the brain of the patient, and we have the wire that is going below the skin, so you don't see the wire, to a pacemaker that is located over here. And then the patient is coming to the neurological clinic, and the poor neurologist have now to find the optimal parameter in order to cure the patient. And he has 4 contacts to play between them, and so it is a 4 contacts. He has many other ways to change the parameter of the stimulation, the voltage, the pulse width, the frequency. So eventually, there are many parameters that the neurologist can play and to find the optimal way for the treatment. And neurologists are very good, so they are doing it very well, but then the patient is going home, and the patient is coming back only 3 months later to the clinic. But Parkinson's disease is not fixed for these 3 months of treatment. So eventually, we are not giving the optimal treatment for the patient all the time, because the patient is coming only every 3 months to the clinic. So the way that we came to think about it is actually that we should look for the technology and learn from technology for the optimal way. So of course, one can use open loop system in order to control the temperature of this room, okay? So you can have a fire or fan, but much better, you have a thermostat. And a thermostat, actually, you set the temperature that you would like the room to be over here, and if there is a discrepancy or mismatch between the actual temperature and the setting temperature, then you apply either cooling or heating to the system. So this is closed-loop feedback system. And actually, what we believe that this is eventually the computational goal of the basal ganglia. Because the basal ganglia, the role of the basal ganglia is all the time to look for the mismatch between your prediction and reality. And whenever the reality is worse than predicted, then the basal ganglia are trying to improve, to change your behavioral policy such to that you lead to optimal trade-off between gain and cost in your behavior. So if this is the role of the basal ganglia, if these are the tricks of the basal ganglia, we should be able to exploit it and to use it for human patients. And indeed, actually, what we've done is, again, going back to the monkey. And in the monkey, we've created a model of Parkinson's disease, the same model that we've used 20 years ago for the subthalamic nucleus inactivation. But this time, we treat this Parkinsonian monkey with closed-loop deep brain stimulation. So you can see over here the amount of movement that the Parkinsonian monkey is doing. The Parkinsonian monkey is doing very minimal movement. This is what we give today to our patient. So it clearly helps. The monkey is moving more. But using closed-loop adaptive stimulation, the monkey is much better. And there are many controls. And we see this improvement in many other parameters. So the bottom line of this paper was very simple. Closed-loop different stimulation is superior in ameliorating Parkinson's disease. Very clear cut. So what we should do now, actually, it is very clear from our point of view. We should find the optimal multi-level system that will be able to adjust in order to cure our patient. We should do it in human patient, and it would be very easy to convince the ethical committee, because if we close the loop, we can always open it and come back for the open loop stimulation with the standard of today. But then maybe we should think about other disease. And the other disease are the mental disorder. And the most severe mental disorder for me is schizophrenia. 1% of the population, starting at the age of 25, and we don't offer their treatment. We can control their positive signs, okay? So we can avoid them. They are not shouting in the street, but we put them in hostel and we are not giving them the option to go back to society. And this is for a monkey model. This is for a monkey model of schizophrenia, that we have some kind of what we call the neural signature. And actually, I believe that if we have a neural signature of the negative symptom of schizophrenia, then we can move and even try first in the monkey and then in the human patient. It is not easy what I'm suggesting. I'm suggesting now to go for a psychosurgery. If I'll be successful in the monkey, then the next step probably should be try it on human patient. And we are very aware of the really terrible history of the frontal lobotomy. Frontal lobotomy was done because of the same frustration that we are facing today. Even in the 50s, there have been too many schizophrenic patients that society was unable to cure them. And these people that today we treat them as devils, but reading their paper and reading their memory, they were really trying to help the patient by using the frontal lobotomy in order to cure schizophrenia. And today we think that this should not be done and it should not be cured. So how can we learn the mistake from the past and avoid it when we'll offer psychosurgery in the future? So I think, yes, being very aware of this problem, nevertheless, we should do it. And we should do it because brain disorder or mental disorder are a major burden to our society. They are not only economically, these are the main source of suffering. It is not a cardiac disease or a kidney disease that it is used at fight with the disease. The mental disorder patient is losing itself, okay? Is losing the self, is losing the ani, the identity of himself, and therefore, for me, these are the most devastating disease that we should offer some kind of treatment. And we know today that pharmacologically is not working good enough. And this is quite clear. Brain main activity is carried by electrical signal. So from time to time, we can use pharmacology. But clearly, if we'd like to interrupt with the brain, then we should use electrical activity. And this is what is written over here. And therefore, using a deep brain stimulation should work much better. And finally, today, okay, unlike the frontal lobotomy, deep brain stimulation procedures are precise, reversible, and adjustable. There are minimal side effects in good hands, no bleeding, no infection, and therefore they are, in my opinion, the optimal way to move forward in treatment of this patient with mental disorder. So this is the last slide, and again, as I said, frontal lobotomy is considered as a kind of a treatment that should not be tried anymore, okay? And I completely agree. And this is from, again, it was said that, let's say by Tom Waits, that I'd rather have a bottle in front of me than a frontal lobotomy. And I would say, yes, okay, but would I, or one that I care for, would have a severe a mental disorder, I would really think about closed-loop adaptive deep brain stimulation because they are reversible and adjustable. They have minimal side effects. They are based on, this is the last one, they are based on good understanding of the brain. And I think this is the ethical point of view. We, as society, today should take the patient point of view, not the society point of view. So we don't care about the caregiver or the family. We will care about the patient. And with good evidence-based medicine, we'll be able to do a good job and help our patient. Many thanks for your attention.
Two fast questions. Yes.
Idan mentioned at the beginning that in the next generation we will probably need like 100 years. My question is, would you use this method also for senility?
First of all, there are already on
Hagai, sorry, can you repeat the question? I don't think that
the question was if we use this method for senility. There is already ongoing trial in Toronto of using similar method, not adaptive, but deep brain stimulation for Alzheimer. Okay? So people are already trying it, and I would believe, again, I am much more concerned with schizophrenia than with Alzheimer, okay? Because I would say, yeah, although most of us are already in the age that are more in risk for Alzheimer than in schizophrenia, we as society are offering much better treatment for Alzheimer patients than for schizophrenia. But yes, I would use it for most brain disorder. And then, actually, I think that this is a very tricky question. We would use it in order to augment cognition of normal, of what we call normal. This is much beyond my ability to answer, but so in the meantime, I'm just trying to cure schizophrenia. Yes. So Brainwave is a company that is using transmagnetic stimulation in order to do, and we are very familiar and we are friends, and of course the dream is to do it in a non-invasive way. I would say that it will take much more time because the ability to use non-invasive deep brain stimulation is still very, very limited. So maybe in the far away we'll be able to use different tricks without invasive therapy. I would say that in the next generation, we should go to such invasive therapy, but clearly in mind, the less invasive the method, the better it is.
Another question until we succeed to
you mentioned DBS as a method, and you mentioned pharmacology as a second method. Can you say some words about stem cells?
So stem cell, probably many of you have heard about the success or the artificial success that has been reported 20, 25 years ago with treating Parkinson's disease with stem cells. So giving the patient stem cells that will manufacture their dopamine. We don't need to give them pills. They will be able to use their own stem cells. Unfortunately, these studies have been declared as a failure. It is not working because the stem cells were doing much more dopamine than necessary, and many of these patients actually need deep brain stimulation. So today, at the present technology, stem cell therapy is still very, very experimental. It is somehow in the midline between this deep brain stimulation and pharma treatment, and I think that we are waiting for the future. It is very far being based in human theater.
Thank you very much, Hagai. Thank you. So our next speaker is Professor Olaf Lamke from EPFL, Switzerland. Olaf is a visionary, if you will see soon. Thank you for coming such a long way. Not so long.
Very close, very close. Okay, I'm happy to be here. and tell you about research that we're doing at a new center at my university in Switzerland, which is dedicated actually to augmenting cognition, but also mobility and perceptions, a center for neuroprosthetics. What I would like to do today is tell you about two different aspects of what we're doing in my particular research laboratory. One part is science, so we're going to talk about how the body is represented in the brain, how have we and other researchers looked at this in the past, and then one particular aspect that came in the last talk, that the notion of self was mentioned. So we believe in the lab that understanding this body representation will be very helpful also to understand scientifically what it means to have a self. And I'll give a definition in the next slide. And then within this center, what really I try to develop, and with my colleagues there, is a form of cognitive neuroprosthetics that doesn't really exist yet, but we want to basically, by what we understand here, manipulating, controlling aspects of the body representation of relevance for self-consciousness, project this to machines, artificial limbs, and robots, eventually, that we've also seen in the first talk to be mentioned. So the subject of self in cognitive neuroscience, it has been studied, as you know, for 2,000 years. Philosophers initially, psychologists very recently, and now neuroscientists, particular cognitive neuroscientists and computational neuroscientists are looking at the problem of the self and the related aspect of consciousness. But it's one of those things that everybody in the room here knows what it is to have or be a self, to be somebody, but when you then have to define it, or I have to define it, it's kind of a tricky thing that is like consciousness, very, very difficult actually to define, and then that everybody would agree on. So this is one definition that I find very helpful to just get started. The self is you can see two aspects. First of all, physically I'm different from Amir, who is sitting in the first row. So I'm different from other social beings from the same species. I'm also different from the environment, this chair, for example. So the self is this entity that is really different, or we have this conscious experience that we're different than people and objects around us. But then there is this mystical thing that we're this entity who is having thoughts, who can reflect about myself, about other people, and also actions. These are my actions. These are my left-hand movements. I'm the one generating these. But of course, it's my brain generating these. So what is it in the brain that leads to this sensation? Well, that it's actually me, and what is this me that is doing this? Cognitive neuroscientists, and this would take up the next 13 minutes, I think, at least, if I would go through this. Don't worry, obviously I will not do this, but people have studied visual recognition. If you look each morning in the mirror, for example, people have thought that this is a nice way to understand the self. They have looked at memory, thought, language, intentions, social aspects, but all these, in my opinion, just look at sub-issues of the problem. We started looking at one particular sub-aspect of the problem of the self, which is body processing. How do I move my hand? How do I feel my body? And what's the relevant for the self? And I show you one illusion instead of more words, how this can be tested actually in the research lab. And actually, a notion that we all have that this is my hand or this is your hand in the audience, you would say probably, well, I can't get it wrong that this is my hand and not somebody else's hand. But neurological damage actually suggests that this is a frequent disorder, a relatively frequent disorder in the clinic, but this is even more striking in all of us. We could induce this illusion very quickly that we don't recognize our own hand as being our hand. So basically what's happening here in the video is this is the subject that is studied. There is a screen here that occludes his hand. What you will see is that the experimenter applies a touch cue here, but at the same time that this ridiculously looking fake hand, could be a robotic hand in the near future, there is another touch cue that is applied, but that is only seen, okay? So there's a conflict with respect to what you see in real life, called the rubber hand illusion. So they're even having fun in the research lab. That's very good. Maybe he has not so much fun. If you repeat this experiment, I show it one more time, not because it's so great, but it's really, if you look, the aggressor is coming from here. But what is introduced is a link, a trick. The brain is tricked to believe that this fake hand that he actually is his left hand, right? He should pull away this hand because the aggressor is coming from here. He pulls away this hand because the brain creates erroneously links between this hand and this hand. And in normal life, of course, if you see and feel a touch cue, it's always at the same position. what the researchers do here in the rubber hand illusion, they create a conflict. They put 20 centimeters in between, and then if you feel the touch at the same time that you see it, you believe that this is your hand. So this is called the rubber hand illusion, and there's two illusions. Why is this called an illusion? Well, the fake arm, is this hand here, feels like your own hand. So if you ask people to rate that the fake hand feels like my real hand, this is rated very highly in this condition. Also, you feel the cue that you see applied, you feel it really as if it was applied to your real hand. Okay, so you get these two things very quickly wrong. 1 minute of stroking induces this. There is a recalibration. If you're asked to point towards your real hand, you make errors. Your brain does not find its own left hand anymore after 1 minute of stroking. Although on everyday basis we always think that this should always be correct. It is not. And the brain regions involved, I briefly showed you them here. This is functional fMRI that was introduced, can be used to find and define the brain regions involved in this. Now what we have been interested in the lab, I will be brief on this, is define or do two things. First of all, we want to induce the illusion in an automatized way. We don't need anybody else stroking. We want to have a simple stimulation method applying the stimulus. Then we provide the virtual hands, not fake hands, over a virtual reality display, and then we can do as many conditions for as long as we want, and we have been able to show that much stronger illusions can be induced in this state. We can also go on to move to analyze brain signals online while the subjects are involved in this paradigm, and we have recently built, together with the computational neuroscience group at EPFL, a Bayesian model, a model that accounts for how the subject will behave. In our particular interest here, what is perceived as my hand or not. So it's not the subject who controls it, it's us as experimenters who can control how the subject will react in those methods. But I started out by trying to come up with a model for the self, this entity to which things, perceptions, and actions are ascribed. But what I've manipulated in the rubber hand illusion is actually how a hand is ascribed to this entity, to me, yes or no. So we're not studying the entity, actually. So in this line of work, we actually go a step further, is the main part of the lab, and we try to come up with a version, not a rubber hand illusion, but a sort of rubber body illusion, a full body version. Can we do similar illusions for a full body? And so what we developed is a sort of avatar virtual reality setup. So you see a camera here. Now the experimenter is standing here. The person with a white shirt is now our experimental subject, and now the subject will not receive stimuli on the hand, but on the back. As you can see here, I think there's a short video on this as well. There's also more of this on YouTube if you type virtual out-of-body experience. So there's a stroking stimulus now applied here. So this is just like the stroking stimulus at the hand, but now what the subject is seeing, because the subject is wearing a head-mounted display, goggles, and all the subject is seeing is what the camera is seeing. So the subject is standing here, but actually sees the body, the own body, 2 meters in front. So there's the same distance that we had between the two hands that we now exploit for the full body. And you're not surprised maybe at this point to find that if you apply the stroking here at the same time, then you see it, there is a very strong illusion that actually this avatar's body or this virtual body that you see is your body. So what works for the hand now also works for the body. And I was very happy because if you imagine we have to induce stroking and automatized stroking patterns for each finger, for the hand, for the arm, we would have to do a lot of stroking devices. This is a minimal version that seems to shift and distort our own full body representation. Okay, because if you change this representation, the hand representation is also likely to be changed. I mentioned there is a recalibration. So how well are subjects localizing their body? What we were actually to find here is that this person will not indicate where the self is localized, namely here, but it will be drifted several tenths of centimeters in a predictable direction, a recalibration towards the avatar's body. So the brain starts really identifying with this body, self-consciousness, but also we can measure this behaviorally, that the brain starts thinking to be 2 meters in front. We have done several other studies looking at what happens to brain processing during this illusion. Just two quick things. If we apply a touch cue to the back, you perceive them less well. If you apply a painful stimulus to the body of the experimental subjects, they endure more pain. There is pain analgesia. So these also for applications to patients are interesting conditions. Time is running fast, so I skipped. There was a robotic setup that we developed here. using an fMRI scanner. We built a robotic system here replacing the mattress that allowed us to do our condition also using a brain imaging. What we could find is that there's a dedicated region here in red that is activated and distinguishes whether my brain localizes me here or at Idan's position or at another person's position. Depending how far this is, how this is manipulated, this brain activity puts us at a certain position in space. So having normal activity here puts me into my body in the first place, and this is an ongoing active brain process. This is not just this region. You see other regions shown here in blue are also activated. And this was interesting for me. I'm an MD by training, neurologist. We initially started launching this line of research by studying patients with so-called out-of-body experience, which have exactly what we've tried to induce by these stimulation techniques. Namely, patients with out-of-body experiences feel to be at a distance of 2 to 3 meters from their body. So this is actually holding this system between neurological data and with data from cognitive neuroscience. The self is often considered, this is the science conclusion, a very mysterious or greatest mystery of the human mind. Actually, these data show that we should not wait another 60 years before studying it. It actually seems to be quite simple to study it, more simple than we thought. And what I want to focus on in the next part is how can we use and exploit this capacity to control our full body representation in order to augment and control artificial robots and bodies. So this comes then to the part of cognitive neuroprosthetics. The projection of self-consciousness, these aspects that I've just presented to you, self-identification with the body and calibration of where I am in space to computer-generated avatars, robots eventually, and probably what will happen first, prosthetic devices and artificial limbs. But I will start first with telling you about a project that is actually ongoing. The first people actually on this planet who are already using and extending their bodies to incorporate tools are surgeons who are using minimally invasive surgery devices. This is a system that we have available in Geneva, where the surgeons actually stop operating, and what we're studying, you can see a system here, is when the surgeon sitting here is driving a robot that is inside a patient's body. You see the surgeon sitting here. Normally the surgeons used to have their hands inside a patient's body. Now all that is inside the body is this minimally invasive robot that is carrying out the operation. There will be a video soon. What we are interested in is to follow up actually on data that come from neuroscience, which have shown that once you hold a tool in your hand, like this laser pointer, it becomes part of your body. The brain starts treating the tip of the tool as the tip of my index finger. Now with these huge robotic tools, we have the possibility to see whether this metaphor actually is consolidated also by neuroscientific data. This is activity in parietal cortex, and I've used this system myself. It's very intuitive. Seeing these devices that you will see in a second feels like as if you are manipulating with your fingers in that different entity. But what does this mean? These are new tools that we never used before. One prediction for this meeting could be that there will be new brain regions already particularly at work, and I'll stop this nasty video in a second, but this is how the surgeons operate now and will probably operate in the future, and you could operate, of course, a patient at a far distance. But what we are interested here from a neuroscientific point of view is this going to be a new kind of hand and a new function and a new brain region in parietal cortex. More down to earth, maybe phantom limb patients and amputee patients, like this patient with a right upper limb amputation, feels the persistence of a hand. So there's ownership. This is not just a random hand. This is his hand received like this, and he feels this hand. There's touch cues. Now, how we know already that this presence of these phantom limb sensations that sometimes lead to phantom limb pain actually are linked to differences in how your brain is organized here in primary somatosensory cortex. Now, I've mentioned before that we have this automatized version of the rubber hand illusion, and there is work here by Todd Kuiken from the University of Chicago, where automatized form haptically controlled rubber hand illusions are induced in phantom limb patients and amputee patients. Look at this patient, upper limb amputation. There is the stump here. Tactile cues are applied here in an automatized fashion, while the fake hand, a prosthetic hand, is receiving touch cues. So this line of research will actually, once these are fully connected to the human body, be able, whenever the artificial hand will touch a certain device, will be sent over these interface structures to brain structures that actually record and encode in you and me when we really have our hand touching a physical entity. So this is yet another version. So in my concept, the right design of this artificial limb will be very similar to the right design for robotic surgery. Both are tools that the brain very easily incorporates into its body representation. And if this is incorporated, we'll probably have new functions, because we can then start also in a robot, in the surgery case, for example, not just have one arm, but several arms. 30 seconds. Okay, so I'll be finished after this. I just wanted to finish also with entertainment and maybe some industry applications. The two applications that I mentioned were for the upper limb. One application that I see also is computer gaming and video conferencing, for example. If you think about the projection of the avatar, or of self-consciousness towards the avatar that you've seen on the video projection, what about video conferencing, where everybody would project selfhood to an avatar, and one could meet and interact into this scenario? Actually, in computer gaming, this is ongoing in so-called first-person perspective games. And one idea that we're pursuing, not just, of course, in this line, but also with respect to robots and exoskeletons that will be able to support and human walkers, is that either in the simulated way, you see there is once in a while you see the hand, a perspective computer game, you see that this is kind of exactly the same scenario that I've shown you, that if we apply this additional stroking, the brain starts believing that you are actually this red figure that in this computer game, first-person perspective, is actually your body. So you could project this to this one body, but also to additional bodies. And I thank you for your attention and look forward to your questions.
The future. So if you can arrange yourself, then I have a few questions, one or two questions from the audience. Sure. Well, I wanted to ask you, do you think that within 2 or 3 years in the President Conference, I will invite the avatar of yours, you will sit in Switzerland, and then we'll all feel, and you will feel that you're personally here.
Well, I always thought Israel is the country of technology, but let me tell you how we do PhD defenses in Switzerland. So many people don't come actually at this video conference for PhD defenses, which is really increasing a lot. So sometimes if the video conference is good, you actually do have the feeling that that person is there. Of course, this is my part, but I think if these kind of technologies are improved, and people are giving up on the idea that everybody really has to physically be there to do such evaluations and many other interactions, I think this will be more and more happening. I think video conferencing and how we interact instead of being on the telephone is just one example. What is missing is the neuroscience and the computational part of it.
Yes, sir. Have I understood you correctly when you say that the tools which cannot be integrated into our own personal bodily image are, in a sense, impossible, therefore we could not have 4 arms?
I think we have to see what is not possible. There will certainly be certain tools that are not possible to incorporate. On the robotic tools, it looks like pretty impossible, but once you use the system, the robot feels just like an arm. An interesting question for research is how many arms can our brain actually incorporate and represent in the brain? I think we may not be limited to 2. And Hollywood shows us non-scientific examples, of course, of this, but I think the human brain probably has a power to incorporate more than just 4 limbs. Actually, there's patient examples, I probably don't have time, but there's a case of pseudonumerary phantom limbs after brain damage. So these patients will receive 2 or 3 left arms after brain damage. If it's necessary to lift devices, why not? I mean, if you think about a crane and what some of these robots do, they're not built on of course the human body, but I think it's a nice potential that we don't exploit it.
Thank you very much, Robert. Very the last young speaker is Dr. Amir Al-Mehdi. He's a newcomer, relatively newcomer to the new center that I mentioned in Jerusalem, the Edmund and Lily Safra Center for Brain Sciences there. As I mentioned, we are now building a new center. We have 15 new faculty positions, which is fantastic for brain research, and actually a little bit more now, and Amir is one of them. Thank you for coming.
Well, it's a pleasure to be here. I'm a newcomer, but actually I'm an all-comer because I studied in this program, so it's a huge pleasure and honor to speak in front of my teachers, Chagai and Idan, and in front of scientists like Olaf and Shimon, and in this presidential conference. since I'm young, I would only try to entertain you a little bit for 15 minutes and see how far we get. But I'm going to talk about a serious issue. And I'm going to talk about seeing with the ears, hands, and bionic eyes. And I'm going to talk about the problem of blindness. We know that there are 40 million people that are blind worldwide, severe visual impairments. And when I'm talking about severe, I'm talking about real difficulty to see anything that is on the screen is increasing in the entire world. We're talking about over 300 million people, especially with age, diabetes, etc. So this is also a serious issue. And we also use it, and I'm standing here, but actually I'm representing my team, and I hope to highlight some of the people that are contributing to this work. We are also will try to use it as a tool to understand the brain better. And I would actually start, this is just sound check. I would actually start with this. I think as a first slide it will be a little bit vague, but I think very quickly during the talk you would see where I'm heading. So the common wisdom, one very central thing that if you still open in 2012 any neuroscience textbook, is that the brain is a sensory-specific machine. So we know, for example, we have a brain-dedicated areas in the back of our brain that is dedicated to vision. Then here we have a brain part and lobe that is dedicated to audition, and we have for touch and the body, like we saw in Olaf's talk. And this is not just a theoretical thing and a theoretical theme, but also a practical theme, because, for example, we have the Nobel Prize, part of the Nobel Prize to Hubel and Wiesel was because of their better understanding of critical periods, and the idea that if you don't get an input to one eye during a critical period or a sensitive period, you would never be able to see again, even if you fix your problem. And if you didn't get the input for both eyes, you would never, it doesn't matter what we will do, what magic, what medicine, whatever we will do, this person would never be able to see. What we suggest is that actually there is a different organization principle to the brain that offers some hope for visual rehabilitation, but to rehabilitation in general. And basically, this common wisdom suggests that the brain is a highly flexible, sensory-independent task machine. So the critical thing is, what are the tasks the brain is facing? And it will be able to adapt, but only with the right technologies and training. And these critical periods may be reopened and visual abilities restored. Okay, so this is the underground current of what I'm going to talk about today while trying to entertain you. Why do we have this strange way of looking at the brain? I don't have time to explore all the evidence from our lab and from other labs, but I will highlight one example. For example, what you see here is an area in the back of our brain that Idan mentioned. Reading developed about 5,000 years ago, and people like Stanislas Dehaene and Laurent Cohen found that part of the visual system in the back of our brain is dedicated to process reading, like reading this text on the slide or book or whatever. And this is what is amazing, is that it doesn't matter which culture you're coming from, what system, the activation will be highly precise, less than half a centimeter across the entire people if you do some adjustment of the size of the brain, etc. So this is highly replicable phenomena. It doesn't matter how you read, in which language. While you're doing the vision, you have the visual system light up in a very precise area. And what Lior Reich in our team showed is that when you give blind individuals that were born blind, so they never saw one photon of light in their life, read using touch, using Braille, then it's not the somatosensory system that is specifically recruited. It's the information passed through there, but the main brain area that is doing it is the same visual so-called work-from area. So actually, this is not a visual area. It's an illusion because vision is so good in doing reading, but if you read it during a different modality, it will be exactly the same activation. And actually, this is an image, if we show it to any visual workflow or visual scientist, he would say this is a sighted person reading by vision. But no, this image actually is the group results of all the blind that read using touch, using the hand. So maybe the reading is really a bizarre example. You know, maybe this is just one example. But can we generalize it to other functions? Let's start in vision. And in order to do this, I would have to tell you one thing that probably you already know after Shimon's talk, but I think it's very important because most of the people would do a parallel between how our visual system works and a camera. Okay, so you have the lenses and you have increasing the light and decreasing the light, et cetera, et cetera. So the periphery is very similar. But our system in the brain, our visual system is very different. And it's creating, in a very active way, our images that we see. And what is outside in the world is only part of the story. So for example, how many of you, if you saw it for the first time, see, and this is, for 5 minutes, we'll have an interactive thing. Okay, so we need your participation. See here black images on white background. Just raise your hand. So excellent, you're not blind, so that's already good. Now, those of you who can see only black patches on white background, keep your hand up. Those of you who can see something else, you can leave your hand. So about a third of the audience can see here only black patches on white background. Now, if I will tell you, to those people, that between each two patches there is actually a letter, now your visual word form would start kicking in and would read this, and what is written here? Lift. Now everybody can see it? Is there anyone that you still can't? So you see it, perfect. So I can move to the next slide. So the bottom line is that something changed in the way you process the world and you create an image of the word lift here. So it's an active thing. Another example which I really like because it happened to me spontaneously. After that I read about it, but apparently this FedEx guy, so again you read this, you have your visual word form area working. But actually the guy that, so how, all of you can read this, right? Any of you can see, but don't say anything loud. Anything of you can see something in addition? Okay, so about half of the audience. So what happened to me is that you look on this and you see only FedEx, and then after 100 times you know that I sent paper and they are rejected, and we send them again and they're rejected again. And I see the truck on the street and I just saw the FedEx. One day I realized that they hide between the E and the X an arrow. And actually they were winning a design award for this because it actually would tell you, okay, we bring your stuff in time, et cetera, okay? So again, and now those of you, did anyone here didn't see the arrow before in the audience? So about half of the audience didn't see. So actually, just like Idan said, at this moment, I changed your brain. Because now if you want to ignore this arrow, it's not doable. And actually, even more so, each time now you go in the street and see this truck, you remember me in this boring lecture. Okay, last example is this example, and again, it's dedicated, it's to show you that we have a dedicated brain area to process faces. But this dedicated brain area, it's not just that we have a brain area or a network that processes faces, it's a very particular network that was carved during evolution. And the brain actively creates this. So for example, here you can see that these two Mona Lisa, all of you can recognize this is Mona Lisa's, right? And some of you which have really good vision and active visual system might see some changes, differences between, you know, we had here the ציור שבוי לילד in, you know, to find the tiny differences. So, but there is some differences in the mouth and in the eyes. And actually what I'm doing, what I will do, people don't really believe this. Well, this is a known phenomena, but people that see it for the first time don't believe it. So I'm rotating only 90 degrees, and now I'm fully rotating. So this is exactly the same image like this, okay? And the point here is that now this is a really ugly Mona Lisa, and this is a really pretty Mona Lisa, okay? And even though I'm going to tell you this is exactly the same, now you can't see the ugly Mona Lisa anymore. You can see it's a slightly different Mona Lisa. This is because evolution created this network for upright faces, because this is how we see people. You know, we go in New York in 2 a.m. in the 80s. We need to know if this guy is going to kill us or we need to go to the other side of the street, but then maybe the car will go over us, et cetera, et cetera. So the point is that we actively create the images in our visual system. So if this is true, maybe we can use it to help to blind people. And I won't have time to go over all of this, but the pioneer of this field was Paul Bacharita. in the tactile domain and in general, Peter Mayer in the auditory domain. But the idea is that you wear a camera. The camera would see instead of you. You would hear or being touched, like in Olaf's case and in our case, in an auditory case. And your brain would create the images. Okay? That's the theory behind it. And if you would create these images, you would see, quote unquote. Now, if you want to see this setup, you're welcome actually to the LSEC and Hebrew University booth. We are going to show this as well as other technologies to blind, if I don't have time to show you all of this. But the bottom line is that using a set of rules, and these rules can be very simple, we can represent all the pixels in sound, okay? It's very difficult to understand, but so I will just give you, I would skip all this, but I will give you just one example, or two examples. So for example, here we have a very simple image. We have this rectangle. So if something is black, you don't hear anything. If something is white, we have sound. If the sound is in the upper part, you hear high tones, beep, beep, beep. And the sounds, in a way, represent the topography in vision. This is not how usually the auditory system works, but in using this algorithm, it can work, okay? Now, also concepts like if I'm fat or thin can be represented very easily. In this case, fat line or thin line, okay? And the fat line is longer in time, and as it got thinner and thinner, it's shorter and shorter in time, okay? So these simple rules basically give you a way to interpret the sounds. Can the blind now really learn? Actually, what I'm doing usually here, we don't have enough time, but I would actually present to you a word in English of scanning the image from left to right. Okay, so for example, how many letters we have in this word? I would play it 2 more times. Can anyone tell me how many letters? 3, fantastic. Can you tell me something else about these letters? Fantastic, you are very good. So the first and the last one is exactly the same. Now, since there is some hope, although I didn't do the training because I don't have time. Very close, very close. So W is the first, and the first and last repeats. You are fantastic. Although I didn't train you, you were able to read a word. By the way, I'm going to talk for half a second about bionic eyes. So bionic eyes is just tools like Hagai presented to go inside the system in some cases. For example, if you lose your receptors, and stimulated. The most advanced bionic eyes we have today can do reading of 1 letter or 1 word after 1 year in several minutes, or in 1 or 2 minutes. So it shows you just how intuitive it can be. Now, it's not only what is on the screen, it can also tell you that this word is now up on the screen and now low on the screen. So where the things are is very important because we want to act upon them. And finally, it can also tell you the sizes. So if you're very good, you can hear it's the same thing, just smaller and cuter maybe. Now, more seriously, what can the blind do with these things? So for example, first they just learn the rules. They come to the lab for 40 hours or 70 hours. Then they learn lines, etc., and junctions. Then they can recognize this is a phase and this is a tool, but they can't say which tool. And then they can also say which object it is, and even which facial expression. So I would show you here, for example, just the gist of this program, how we teach blind to, for example, do, like I did for you, teaching to read, simple things. In this case, this is a congenitally blind.
Okay.
Learning to, first of all, the features of faces in front of the computer.
מה זה, זה גם? וואי, נראה לי שומעים את העיניים ואת האף.
יפה. ואתה שומע פה אולי עוד משהו?
שנייה. נראה לי שגם הגבות מופיעות.
מעולה, כל הכבוד. בוא תנסה עכשיו להגיד לי.
העצוב זה השני.
יפה מאוד.
Then we move from 2D training to real-life training. And you can, one question that people ask, if they are doing it, they don't be able to hear again. But our brain is actually amazing. It can switch in milliseconds from one thing to the other. So you can see that she is talking with us while she's touching Ella's face, while she's listening to the sounds in the training phase. Now she's not touching Ella anymore, the pitch is at least this project, but looking at her, and she needs to know what she's doing. Okay, and she can even do facial expressions. So you hear this bizarre sound, now you can't say anything about it. But if you come to the lab, and that's actually universal, there was no person, late blind, sighted, that came and wasn't able to learn this. 40 to 70 hours. So not too long, several weeks. Depends how much energy you have. And now generalization, a different person will come, and she will still be able to do it. Okay, 1 minute. Just to recap, what's going on in the brain while they learn to do this? So what's going on is quite amazing. And actually what we do is, now you're experts on fMRI and EEG and TMS after this talk, we actually scan their brain while their sounds are meaningless. Then we scan their brain after 2 hours of training, so it's not enough to create new synapses. So it's how the brain learns, like you did, without creating proteins and synapses, etc. Then we train them for 40 to 7 hours and scan their brain again and in several other points, and we see how actually the brain completely changes and rewire. 2 very quick examples. One, this is again the visual word form area, that we shouldn't call them anymore visual word form area, we should call them word form area, because we do it in Braille. When the sounds are meaningless, these auditory sounds, this area is not activated. This is an example of one person. But now, when we teach the sound to these individuals, then it's activated both by Braille and by the soundscape. The last example I'm going to show you is the Object Recognition Center. Also from the Weizmann Institute, we have Rafi Malach that found that we have a parallel of the monkey ventral stream IT LOC that activates each time you see an object. What's going on when the subjects learn to recognize objects, tools, this laptop, etc.? Then this area in the beginning, the activation all goes to the auditory cortex, and it's unspecific, but once we recognize objects, it goes exactly to the same network. So actually, we're talking again about a task machinery to decipher, for example, the 2D or 3D surfaces of objects and recognize what they are. Part of the effort of our team is to build new devices. So here we try to create, color vision for the blind, and also I won't show it via music. I won't show all the details, but blind can also actually act upon it very accurately, just like in vision, to develop new cane for the blind that can sense. And again, you are welcome to test it and train on it on the booth, on the Hebrew University LSEC booth. And finally, this is the last slide. We are thinking about using it to teach the brain and speed up the qualia that is being created by neuroprosthesis by combining it with this type of training, okay? So I would finish here and thank my team. I highlight some of the individuals that contributed, but actually all of them contributed immensely to this and other projects, to some funding agency, and to you for your attention.